And the recording is on. It's week 5. We're going to be talking about importing, exporting, and cleaning data today. Do we have any questions? Maybe about week 4 materials before we get started? Cool. Then let's go ahead and get started. So today's theme, we're going to be talking about data custodian work. These are issues around things like getting data into R and out of R and making it analytically ready for whatever kind of calculations we might be doing. This is things like working directories and projects, importing and exporting data using these 2 packages, Reader and Haven, cleaning and reshaping data using the Tidier package, and dates and times using the Lubridate package, as well as controlling factor variables with the forecast package. So we're going to start with directories. You may recall that the working directory is where R will look for and save things by default. You can find out what it is using the function getWD, standing for get work directory. On my computer, when I knit these slides, when I knitted, I said, the past tense of knit is knit? Question mark? It's not. It is knitted? No, it's just knit. It is. That's okay. I'm Southern. I don't know grammar. On my computer, when I knit these slides, it happened to be C, users, Briha, OneDrive, documents, the course website, the tab for the course, lectures, and week 5. You can change your working directory using the setWD function, and then specify what directory you'd like to have be the default where everything goes directory. So something like setWD, and then the directory will be equal to, and you specify your working directory path. Some suggestions of best practice is first, Markdown files use their current directory as the working directory, so you can just put everything you need in there. For larger projects, I think I might have mentioned this before, but instead of setting a working directory, it's usually better to use RStudio projects to manage working directories. So anything that I think will have more than like 2 or 3 R scripts in it, I tend to use an RStudio project. And particularly for Windows users, if you copy a path from the File Explorer, make sure to change the backslashes to // for the file paths. I'm not quite sure why this is the case, that it goes the wrong direction, but R can't read it if you just do something like copy address as text. This is not going to be correct because of the slashes. So just keep that in mind. Also, if you need to set a working directory, put setWD at the start of your file so that someone using another computer knows they need to modify it. So I'm saying this just in that rare case. I wouldn't recommend doing this, and I'll talk about in a second what you can do instead. So a better way to deal with working directories is RStudio's project feature that's in the top right dropdown. So I'll show you now. It's this button up here, and you can make a new project. And you can specify folders that are like already a folder for your directory, and it will just create an RStudio project in there. This is also a place where you can set up really easy version control if you're already familiar with using Git or something like that. Okay. So the advantages of using the projects function, the projects feature of RStudio is you can set your working directory to the project directory automatically when you open the project. So you don't have to worry about where things are. It remembers the objects in your workspace, your command history, and all that when you reopen the project. So I know maybe particularly for a lot of the new R users, you will have many tabs open of this was my homework for stats class, and this is my homework for this class, and this is a project I was working on, and I just wanted to open it up real quick and see if I could still install ggplot or something. I tend to recommend against doing this, of course, but in projects, maybe that's exactly what you want to happen. You want to be able to open your project and have 3 different scripts already as your tabs right when you open it up. So I'd say in the project's context, I'm not so worried about it. Would recommend against it everywhere else. This also allows you to reduce the risk of intermingling different work using the same variable names in your different environments. So that's why I wanted to caution you against having multiple tabs open, is because it's very easy for a variable name to be a lowercase n or something, and the different RStudio instances, treating them as the same. And last, it's easy to integrate with version control systems. For instance, for this class, in order for me to update the website, I just have to push all my information to my GitHub, and it's really easy when you just have a folder that's an R project already set up. I usually make each RStudio project its own GitHub repository. I've recently taken to like not having a ton of my stuff on GitHub, so I don't know if I have a lot of great examples on my own GitHub besides this class, so maybe you want to check that out. If you're interested in more advanced project management, email me after class for more resources. I'm happy to talk to you about it, but I think it's a little bit outside the scope of this class if something requires something bigger than a project in RStudio. Okay, so once you've set the working directory or you're in an RStudio project, you can refer to folders and files within the working directory using relative paths. That is the relative location of the folder you're working in to other folders in your computer or your instance. For instance, let's say we load ggplot2 and we make this plot using the cars dataset, and we want to save it. Instead of specifying like C:// OneDrive, what have you, you can just say relative to your working directory, I want to put it in the graphics folder and name it this. And RStudio will know that you mean relative to the folder that you're in. Go to the graphics folder there and save it. Okay. Relative paths are really nice because all the locations of loaded and saved files can be changed just by altering the working directory. And actually is part of the reason that version control is so cool. Is like if you wanted to, you could just download this, like all the slides and all the materials for this class, and knit all of it, and it would just run because it's all of the folders are relative to the markdowns that create the class. For instance, here's a screenshot of this folder for this class. And in order to have this picture be on this slide, I just said from the image folder, give me the screenshot relative path picture. And here is my working directory. And then here's the image folder, and it just puts it here. So do we have any questions about relative paths before we move on? Cool. So now we're going to get into talking about importing and exporting data. Okay, so the first thing is there's a lot of special data access packages. If you are working with a popular data source, try Googling to see if there's a devoted R package that already exists for it. So you can load repositories for packages right from the CRAN, which is what we have been doing so far. So when we say like install.packages tidyverse, that's something that's already on R's network for packages. But there are some things that are not on R's network for packages that are just on somebody's GitHub. And you can install those the same way. This is what that code would look like in order to do that. Some popular examples might be the package that Chris Adolph uses to make all of his predicted probability plots. The Richard McElreath Bayesian statistics package is not available on CRAN, and you would install it this way as well. But the special data access packages. So a few examples might be, there's the WDI package for world development indicators from the World Bank. Tidy Census is wildly popular, that just allows you to quickly grab things from the census and American Community Survey after you have like a token for it, and QuantMod for financial data from Yahoo and Fred and all of that. We'll be returning to talking about Tidy Census when we get to geographical data in week 9, I believe. But yeah, if it's a popular data source, highly recommend just checking it out, because if you just use the census API, for instance, sometimes it can be a real hassle. Or if you're not familiar with IPMs, it can be a real hassle. So data will often come to us as a delimited text file. Besides using a special data access package, the easiest way to work with external data is for it to be stored in a delimited text file. That is something like a comma separated values file, a CSV, which we're probably very familiar with, or a tab separated values file. Here's some CSV data from last season's WNBA. And we can tell that it's already a CSV just by the amount of commas. It will come to us as like, the first line will be all of our column names, and then everything below it will be all of the cells. And they're separated just by commas. So we know that things in the first column are date, and then comma will be the separator between the date column and the visitor neutral column. And then in our first row, which will be the second row in our text file, but the first row in our data frame, it'll tell us the date in that same column. And then this comma tells it to go to the next column. Okay, so R has a variety of built-in functions for importing data stored in these text delimited files, like read.table and read.csv. I recommend using the versions in the reader package instead, read_CSV, read_TSV, read_delim. A few things that I like about doing that is it's way faster than using read.csv for reasons that are wildly nerdy. It has to do with how they index all of the rows and columns before they read it. It's a little bit smarter about dates and times. So often will be the case is if you use read.table, it will not understand that something is a date, but read_CSV tries to guess what type of column that you have, and tends to be pretty good about knowing whether or not something is a date. It has handy functions like the problems function that you can run if there's any particular errors, like if you suspect that the data set's going to have 25 columns and you only load it in 2, problems can typically help. And it also provides a loading bar. So it tells you how long something is going to take before it's loaded all the way in. Also, something to note is the vroom package loads data yet faster than read_CSV. Again, partly because of the way that it indexes all of the rows and columns, but it is also not as strong about guessing what the column types are. So if you have like many millions of rows, I would recommend vroom. Otherwise, read_CSV typically gets the job done, but it depends on what you're working with. So here's an example. Let's import some data about song ranks from the Billboard Hot 100 in the year 2000. So we're going to assign to this object Billboard 2000 raw, read_CSV, and then this file that I've saved on my GitHub. So that's a cool thing that I always think is like too futuristic, is that you can just like download things straight through R from the internet without having to like open up Safari or something. I don't know. I think it's neat. But when you use read_CSV, here's what it will return to you. It will tell you how many rows it is read, how many columns it is read, and what it is guessed the columns are. It'll tell you that the delimiter is a comma at this time when they read it. It'll tell you that we have 2 character columns, that is the artist column and the track. We have a few doubles, 66 in fact, that are the year, and it seems like week 1, week 2, week 3, week 4, week 5. We have some logicals, but they are also called like week 66, week 67. That seems curious. I wonder if we'll get into that later today. As well as 1 date and 1 time. Okay. So what was going on with like week 66 and up? If we look at the data for the last few columns, we'll see that there are like tons of NAs in there. And so part of the reason that these have been assigned to be logical and not numeric, like week 65 and up, is that read_CSV will take the first, I think, 100. It might be 1,000, but I think it's 100 just because of the nature of this data. Cells from each column in order to guess what their column is going to be. And since this week 66 doesn't have anything in that first set of like guess columns, it guesses that it's illogical. So it guesses like the minimum amount of information. So this will happen from time to time, even though we know that it's a numeric. One thing that we can do, okay, so I did write in the slides, sorry. So reader uses the values of the first 1,000 rows to guess the type of column. There are not so many songs in the data that charted for 60+ weeks, as you might imagine, because the year 2000 did not have 60+ weeks. Since it encountered no values, reader assumed that week 66 through week 67 were character. To be sure nothing was lost. Yeah, I guess thinking back now. So they recently updated R to 4.2. And there's been some nuances in the changes. Sorry, I'm just thinking out loud. But one thing you can do is use the call types argument to fix something like this. So here what I've done is I've made a string of identifiers for the columns since I already know what the content is going to be. And what it does is it says if the call types is an I, then I'm going to assign it to an integer. If the call types is a C, I'll assign it to character. And if the call types is capital D, I'll assign it to date. And then I just make a vector by pasting this information and hand that vector to the call types argument. And now when I load the data, all of those like week 66 through 76 will be correct. You can also deal with this by adjusting the maximum number of rows used by reader to guess the columns. So here I use read_CSV for some file, and I can say guess_max and hand this argument 5,000 instead of 1,000. Or you could use the read.csv that's in the foreign package. This is the base R alternative. That's slower and a bit dumber, and then just coerce them all afterward. Another alternative would be using Vroom. It does really high speed reading of text files. Some other people would recommend using the data.table fread for reading really big files really quickly. But one advantage of Vroom is you can give it a vector of file names, and it'll read every file and combine them into one data frame. Which I always think is really neat, because sometimes you get a document. Like right now, I'm working with these job flows data. That's a different folder for each state. And using Vroom makes it really easy to just grab something out of each of those folders and then combine them all into one data frame really quickly. This is with the caveat that Vroom has far less error checking than Reader. So it's best to use on files that you've examined first and like have some strong familiarity with. Okay. For XL files, that is .xls or .xlsx, I recommend using the readXL package as well as the writeXL function. For Google Docs spreadsheets, there's the Google Sheets 4 package. Google Sheets 4 has gotten like a lot better, I'd say, in recent years. And it allows you to download things that you're working on in a Google Sheets straight into R. And so that's been really useful recently for me with this project that I'm working on with a bunch of people, where they're constantly updating this particular Google Sheet with these different qualitative coding strategies. One thing you won't get from readXL or Google Sheets 4 is you won't get text formatting and colors and comments or merged cells that you might be used to if you're looking at a Google Sheets document or an Excel. So this means if those kinds of information mean something in your data, you'll need to get creative. If an Excel spreadsheet is giving you a lot of grief, say due to merged cells, the simplest thing is to open them up, manually change them in some way and export to CSV and then import into R. But compare carefully to make sure everything worked. If you need to programmatically work with non-tabular Excel sheets, there are ways to do this, particularly if you need to retain meaningful formatting. There's powerful but complex unpivoter and tidyxl packages that allow you to retain that kind of information. But I tend to think they're pretty fussy. So I do this option kind of a lot when this is my situation. Getting data out of R and into a delimited file is very similar to getting it into R. There's the write_CSV function. So you could say write CSV, a object, probably a data frame that you want to make into a CSV file. And then you specify the path where you would like it to go, naming the document and saying that it's a CSV. So this saved data we pulled off of the web in a file called billboard data is now in my working directory. Exporting to a CSV drops some R metadata, such as whether a variable is a character or a factor. You can save objects into R formats to preserve these kinds of things. So like a .r data file that we discussed in, I think, week 2. There's also the .rds. This is used for single objects. It doesn't save the original object names, but you can say things like write RDS, some old object name, and the path.rds in order to save it somewhere. And then you can load it by assigning to an object this new object name, and then read RDS and wherever this object was saved. The .rda and .rdata formats are used for saving multiple files or like your whole environment, for instance, where the object names are trying to be, you want to preserve them for some reason. So you could say save and then a list of objects and then specify the file path. And it will save that all of those objects in your environment to your working directory. And then you can load them using the load function. Note that this doesn't have an assignment operator. It'll just load those things into your environment. I pretty much always save things as .rdata, but this is only personal preference. When you're asking for help, it is useful to prepare a snippet of your data. And one of the great ways to do this is dput. The dput function is native to R. And you can say dput the first 8 rows of the car's data set, and it will give this little snippet of information. And then you can take that information and assign it to an object, and now it has the qualities of that information. And this makes it really easy for someone to replicate a problem that you're having and help you troubleshoot it. Question? How is dput different from structure? So dput is producing an object that someone else can use, whereas structure is just telling you information about some object. Yeah, of course. Another thing is that dput is the base R version of this. A reprex, short for reproducible example, is the tidyverse version of this, and it tends to include more information, but also takes a little bit more setup. So you might notice now when you're on Stack Overflow saying, I have such and such problem, that you'll see other people's dputs all over the place. So let's say you want to read in data from some other software. You're working with a team of demographers who don't want to give up data for some reason. You can use a package that can just bring in those saved files. So Haven is really great for this. It has a lot of options for bringing in Stata, SPSS, and SAS files, and it's part of the tidyverse family, so it already has that comfort with pipes and that kind of thing. Foreign is also good for Stata and SPSS and Minitab, should you be using Minitab in this year of our Lord 2022. And it's part of base R. For less common formats, I would just say Google it. Stack Overflow has a lot of really great answers for stuff like that. I've yet to encounter a data format with it out in R package to handle it, or at least a clever hack. I've recently been trying to get this data that's only been saved as like PDFs. And there's a package that lets you take tables that are inside of a PDF, and it knows which part of the PDF is a table. So like it could be like a bunch of text and then a table and then a bunch of text, and it will go find the table and then make it into a data frame. I know, I was fascinated because I thought I was gonna have to copy and paste or something. It's really neat. Also, if you encounter a mysterious file extension like a .dat, try opening it with a good text editor first. I recommend using Atom or Sublime or Notepad++ in order to do this. There's a good chance it's actually just raw text with some sort of weird delimiter, like a semicolon or exclamation point or something. And then once you know that, it's something that is in a fixed format and you can coerce R into reading it for you. I had this project when I was a first year that had a .dat file that was tab separated for only some of it. That was super goofy. But luckily my colleague figured out that there was an accompanying Stata file that you could run that would make it the right thing. And then we exported it to that and then loaded it into R. Anyways, let's talk about tidying data. So I'm going to describe some of my initial spot checks when it comes to loading new data. These are not necessarily best practice. This is just kind of my opinion. So the first thing I'd like to check are, did the last rows and columns of the original file make it in? So you may need to use different packages or manually specify some sort of range because some of the last rows or some of the last columns didn't make it in. Or made it in a goofy way, kind of like our billboard data. I've included here a couple of links that are just to data that I think have some of these qualities. The next thing is, are the column names in good shape? You may need to modify the column names argument or fix with rename. Sometimes it makes a lot of sense when you're making the spreadsheet to have a bunch of spaces and emojis or whatever else in your column names. But then when you want to come back and do some sort of data analysis, it's suddenly a big barrier to typing quickly. The next thing is, are there decorative or blank rows or columns to remove? This is like a really interesting holdover to me. For instance, I think that I picked the, oh my goodness, this is a 404. My bad. I'll fix that. But the unionstats.com people, like Barry Hirschman and all that, are terrible for this. I just want to get some data for my thesis. Like, you don't need to put like a paragraph about how this came to at the bottom. You can just send me a thing that says cite us like this, please. But to deal with decorative or blank rows, typically filter or select will get rid of those things. Also, keeping in mind how are missing values represented. In some data sets, they are like familiar with just using NA, and others will just use some sort of space or a blank. Others will use a period, and others will use 999 or 48 or something. And then it's time to use mutate or if else, or perhaps some sort of en masse looping structure in order to get rid of all of those things. Also, are there character data like zip codes that have leading zeros being incorrectly represented as numeric or vice versa? So sometimes there will be zip codes with leading zeros, and since it got read in as a numeric, now they got rid of those zeros. And so we've lost a lot of important information. You can modify the call types argument or use mutate or as.numeric typically. So let's approach some slightly messy data. So the interesting thing about slightly messy data is that it often looks really regular and standard to our eyes. So looking at this information, I feel pretty comfortable about being able to read it correctly. Here's a few programs, and here's some sort of gender distribution of people in those programs. But let's answer some of these questions. What is an observation? An observation here is a group of students from a program of a given gender. What are the variables that we're interested in? Well, we're actually interested then in the program and a respondent's gender. And then what are the values? Our values here for program are Evans School, Arts and Sciences, Public Health, and other. And then the values for gender are woman and man. Whereas, or what's amiss about this is that those are our values for gender, but they are now column headings. And our counts of this information is spread over 2 columns. So while this is easy on the eyes, typically when we want to do statistics or draw a plot or something, this will get in the way. So the tidy version of this data is like not as easy on the eyes, but it is easier to graph. So here, gender has its own column because that's a variable that we're interested in, and count has its own column because that's a variable that we're interested in. And now I'm going to describe to you what's the, I don't know, the ethos of the tidyverse. It's that each variable is a column and each observation is a row. And now this information is ready to throw into a ggplot. Let's look at some much more messy data. Okay. So there's a few things here going on. First, we have the year column, the artist column that seems pretty straightforward. Shout outs to the A-teams. Also, this is last name first. Where's Trace Adkins been at? Then we have track, the time of the song as minutes, seconds. Then the date that it entered the Billboard Hot 100. And each of the week columns tells us the rank of the song in the column. And this goes on for 76 weeks because it includes anything that touched the year 2000. Okay, so something could have started in 99 and then ran on through till May 2000 or something. So let's talk about what are observations in this data. It's weeks since entering the Billboard Hot 100 per song. What are the variables in this data? The year, the artist, the track, the song length, the date it entered the Hot 100, weeks since it first entered. But the weeks since it first entered is now spread over many, many columns. And the rank during the week is also spread over many, many columns. Now, what are the values in this data? Things like the year 2000, 3 Doors Down, the song Kryptonite, the length of the song 3 minutes 53 seconds, when it entered the Billboard Hot 100, the week 3 information, which is information that we're just interested in, is stuck as a column heading, even though it is data that we're interested in. And rank 68 is spread over many columns. So if we want to tidy this data, we probably want long data rather than wide data. So this is an example of wide data where some of the information is housed in the column names rather than entirely as a cell. But if we want tidy data, the values for a single observation are in their own row. The values for a single variable are in their own column. And there's only one value per cell. What one value means is entirely subjective. And one value per cell could mean a whole data set in a cell. For instance, if you're like really into structural equation modeling or something. So why do we want tidy data? Why would it be worth changing this wide data set into something long instead? First, it's easier to understand having many, many rows than many, many columns. Since columns are going to be a bunch of different kinds of information, whereas rows are going to tell us just duplicates of the same kind of information. Long data is actually required for plotting in ggplot2. It might not seem like it, but if you were going to put wide data into ggplot2, using mapping would be very difficult. It's required for many types of statistical procedures, so like HLMs, mixed effects models, that kind of thing. It means there's fewer confusing variable names. Shout outs to Tidy Census, but if you were going to get census data straight from the census, this will happen. And also there's fewer issues with missing values and imbalanced repeated measures in the data. So like all the way out there at week 76, virtually all of the columns or all of the rows except for maybe 2 or 3 are going to be NAs. And we don't necessarily need that to happen. So we'll use the tidier package to provide some functions to tidy up data. This is similar to reshape in Stata or Barstow cases in SPSS. Some of the key functions that we'll be using are pivot longer. This will take a column and then pivots them down to make 2 new columns, which you can name yourself. And the things that it'll take on are things like a name column that stores the original column names in a value column with the values in those original columns. I know I'm saying a lot of jargon words right here, but we'll get some examples as well as you get to approach some in your homework. Pivot wider inverts pivot longer by taking 2 columns and pivoting them up into multiple columns. Again, I know I feel like it's hard to visualize, maybe for a lot of newer R users, what I'm saying, but we'll get there. There's also separate. This will pull apart one column into multiple columns. This is actually pretty common after doing a pivot longer where values are embedded in the column names. There's also extract _ numeric. This does a simple version of this for the common case where you want to grab just the number part of some information. It is deprecated, however, and I wanted to bring it up because I think extract numeric is really great. But now that it's deprecated, it's not going to get any more support from the people who make the tidyverse. Instead, there's a thing called parse number that's in the reader package that does a very similar thing, but instead of separating the columns, it just extracts the number and pastes it into a new column instead of separating the columns themselves. Again, we'll get there. Oh my goodness. This runs just a little bit too low. My bad. So the extract function, I'm going to scooch this over here. The extract function for pivoting a column into multiple sets of columns. There's a good example of Hadley Wickham, who authors the tidyverse, responding to a question on Stack Overflow at this link that gives an example of when you might want to do this. I would say I don't generally run into a situation that I would use extract rather than dealing with the pivot longers and pivot widers, but you might encounter it. So let's show off what pivot longer does. We'll use pivot longer to get the week and rank variables out of their current layout and into two columns. This will cause a big increase in the amount of rows and a big drop in the number of columns. So we'll load the tidier and dplyr packages. We'll assign to the Billboard 2000 object, the Billboard 2000 raw data frame, and then we'll pivot longer all of the columns that start with WK for week. We're going to name that new column week, and then we're going to take the values from that column and call it rank. Okay. So we're taking the values from all of the columns that used to say week 1, week 2, week 3, week 4. And we're going to make a new column that's just called rank and is filled with that information. And then we're going to take all of those column names, week 1, week 2, week 3, week 4, and we're going to make that its own column that's just called week. And it'll give us the numbers from that column. So now if we look at the dimensions of the Billboard 2000 data, we have 24,000 rows and 7 columns. Whereas recall earlier, we had something like 317 rows and goodness, like 100 columns. So starts with is a helper function that's really great when working with pivot longer when we have this very wide data. We could have also used select. So we could instead use pivot longer week 1 through week 76, names to week, values to rank to pull out these contiguous columns. So this will work the same way as like integers when you're using select to grab contiguous columns. Now when we look at the pivoted weeks, we have a single week column, and each row tells us the song week information. So like week 1, Baby Don't Cry by Tupac was rank 87. And then week 2 for this song, it was rank 82, and so on. But how can we pivot even better? So if we look at a summary of our rank column in the Billboard 2000, we'll see that we have the best rank possible is 1. The first quartile is 26. The median's 51. The mean's 51.05. And we have 18,785 NAs in our rank column. So these are observations for weeks since entering the Hot 100 that the song was no longer on the Hot 100. So one thing we can do is use the argument values drop NA equal to true in pivot longer, and this will remove rows with missing ranks. So it's the same setup, but we've added this argument here values drop NA equals true. And when we run summary again, now there's no information about NAs. And the dimensions of our Billboard 2000 object, this data frame, is 5,307 rows with that same 7 columns. So the week column is currently a character. One thing we'll probably want to do is like make it into a number. Tidier provides a convenience function to grab just the numeric information from a column that mixes text and numbers. Actually, I think that parse number is in the reader package. I can't recall. I'll trust the slide. So one thing we can say is assigned to the Billboard 2000 object our Billboard 2000 object. So we're going to be rewriting this information and then mutate. So make a new column called week that's equal to parsing the number of the week column. So we have rewritten both our object and a column within that object. And we look at the summary for week now. We don't have something that says class character and mode character. We can get numeric information about the summary of the weeks. For more sophisticated conversion or pattern checking, we'll need to be using string parsing, which we'll be covering in week 8 of this course. Another thing you could do instead of going through these paces is use the names prefix argument of pivot longer. So we could say the names prefix from the names to, so our names prefix is WK. So we're saying the information that was housed in all of these column names has the same information in front. That's called WK. And we want to get rid of that. That's what this argument is saying. And then we can also say names transform is equal to a list of the week column now as that integer, with week being this one that's being created up here. This is kind of goofy syntax for this. I'm showing you this so that you can use it. I didn't get quite what names prefix is doing. Okay, so when we go back here, see that the week column has these WKs in front. Names prefix says get rid of those WKs. And for the same reason that these WKs are in front here, we were like unable to get the summary. So that's why over here, we took the week column and then parsed the number, which is just give me the number that is apparent in this string to the column. Yeah. Cool. Yes, about names transform. So I don't typically use names transform like this. I tend to make a mutate call after this, but I just wanted to make this clear that this is an option, even though I think that this is kind of convoluted syntax. But that's okay. It somehow seemed like it should be adding the prefix because of how it's named. I'm with you. I feel like it should be called like names drop prefix, just like the values drop NA. But I don't know. I'm not the kind of person that like submits updates to packages. Maybe one day. But now we can see that the week column is an integer. It no longer has this WK out front, and it just has these numbers. So let's see how separate works. The track length column isn't analytically friendly, which is to say that something that has two kinds of information in one cell is not what we enjoy. So let's convert it to a number rather than a character that's in minutes, seconds format. So here we'll assign to the Billboard 2000 object. So again, we're overriding our same data frame. We're going to separate our time column, which has this minutes, seconds format. We're going to separate time into, and we're going to specify which columns we want each of those two new separated columns to be called. So on the left-hand side, minutes, and on the right-hand side, seconds. And then we'll specify what separator we want to separate them with. So it's just the colon between the minutes and the seconds. And then we'll say convert equals true here as well. So that if anything is like a numeric, it'll convert to numeric, even though it used to be a character when those things were in the same column or in the same cell. And then mutate length is equal to the minutes column plus the seconds column divided by 60. And then we're going to get rid of the minutes and seconds columns. And we look at a summary of the length of the songs. We now get them in minutes. So we can say the minimum song is like 2.6 minutes and the maximum one is 7.83. I don't remember what song was that long back then. But the sep argument tells us separate where to split the column into two, where it finds a colon. And then we add the seconds divided by 60 to minutes to produce a numeric length in minutes. Okay. Let's talk about when we would use pivot wider and why we want to. Pivot wider is the opposite of pivot longer. And we just had that use case of pivot longer where we have all these columns and we want to make sure that information makes sense and that we can plot it and that kind of thing. So pivot wider is the opposite of pivot longer, which you use if you have data for the same observation taking up multiple rows. Essentially, yeah, if there's any data that is spread too thin over our columns or multiple data inside of a column. So let's look at this example. We probably want to pivot wider unless we want to plot for some reason each statistic in its own facet. So a common cue to use pivot wider is having measurements of different quantities in the same column. Okay, so here our value column tells us the mean and the median and the standard deviation. And these are all very different kinds of information and should probably be housed in their own columns. Okay, so before pivot wider, let's assign to this object called toLong data, and it's going to be a data frame with this information inside. So it's the same information from this table here. So after pivot wider, the just right data, we'll assign to just right data our toLong data, and then pivot wider the names from our statistic column and the values from our value column. And so now our data looks like this, where our groups A and B are one row, so one observation, and each of the cells have one kind of information inside. So we had this with very different kinds of information in each row, and we pivot it wider in order to have a column for each type. Okay. I'd say we should probably take a 5-minute break here before we get into deeper data preparation things. So at 4:30, we'll get back. Okay, so we're back from our break. Do we have any questions so far? Okay, That sounds like a no. If there are any slow typers out there, that's okay. When it hits the chat, I'll answer the question. Now let's get going. Okay. So let's say we're interested in some sort of critical information to our lives, like whether or not a song hit #1 in the year 2000 on the Billboard Hot 100. So one way we might want to approach this question is to take our Billboard 2000 data and then group by the artist and the track, and then make a new column that's called weeks at #1, which is equal to the sum of the rows when rank was equal to the #1. And peak rank equals if else any of the values in the rank column for a particular artist and track was equal to the #1. And if it was true, then we'll say hit #1. If not, didn't #1. And then we'll ungroup to make sure that our data doesn't keep this structure of artist and track groupings. So a few things to note about what's going on in this piece of code. So first is that the any function is checking to see if any value of rank is equal to 1 for a given artist and track across its entire time in the data set. And ungroup here removes the grouping made by group by, which can typically mess up some later calculations if you don't ungroup. It can also be a troublemaker when you're making plots as well. And now we'll make this really thorough GG plot. That's going to be called Billboard Trajectories, and it's a GG plot that uses our Billboard 2000 data with weeks on the x-axis, ranks on the y-axis. It's grouped by a particular track, and it's colored by the peak rank. Recall peak rank was just whether or not it hit #1 or did not. And it's a line plot, and the size of the line, so like the thickness of the line, is going to be equal to the peak rank. We're going to make them a little bit transparent by setting them all to be 0.4 alpha. And then we're going to rescale the time so that early weeks are more important. Things at the beginning of the year, like kind of set the vibe for the year. So we're going to say scale X, and we're going to take the log of our weeks and set the breaks to from 0 to 70 in increments of 10. And then we're going to take our Y axis and reverse it. So rank #1 is at the top and not the bottom, because typically on plots, things like #1 are at the bottom. We're going to use Theme Classic and make some labels. We're going to make our colors black and red, and the sizes for our peak rank here are going to be equal to 0.25 and 1. And then we're going to move our theme or our legend around a little bit. And so look at this absolute beauty of a plot. This tells us when songs hit #1, they are bright red. There appears to be some censoring around week 20 for songs falling out of the top 50 that I'll probably follow up on sometime in my life when my advisor stops emailing me. And the I wonder, maybe next time I'll make this a 1 instead of a 0. But I don't know, I think it's a pretty interesting little plot. So who had the most weeks at #1? We can take our Billboard 2000 data and then find the distinct combinations of artist, track, and weeks at #1, and then arrange them in descending order of weeks at #1, and then look at the top 7. Why the y-axis does not have constant increase between the weeks? Sure. So here I said scale x log 10. So I've taken the log of the weeks because it is easier to get into the top number one, I reckon, in the beginning of the year. Yeah. Okay. So who spent the most weeks at number one in the year 2000? Destiny's Child spent 11 weeks, and Santana spent 10 weeks. Dude, remember Madonna's Music? This was a bop. I like that one. And Say My Name only got 3 weeks at number one. That doesn't even sound real to me. Anyways, let's talk about days and times. I had a lot of fun playing with this data set for this class. I could spend kind of all day just being like, whoa, Christina Aguilera. Okay. So the Lubridate package makes it really easy to work with dates and times. Prior to Lubridate, when we were in the dark ages, it was really like a hassle to deal with dates and times in R. So I'm really excited to talk about Lubridate. So it allows us to get usable dates. So we have the date the song first charted, but not the dates for later weeks. But we can calculate those now since the data are really tidy. So we can say, override our Billboard 2000 data with our Billboard 2000 data, and then mutate. The date is going to be equal to the date entered plus the week minus 1 times 7. And these are the kinds of fun answers to problems you get to write for your homework also. But what's going on here is it's saying when it first charted, add whatever week it first charted minus 1. So at least for the first week, you'll get a number, and then multiply that by 7. And now we can take our Billboard 2000 data and arrange by the artist, track, and week. So we're going to alphabetize these things. And then after these have been alphabetized, we then see rank in order, descending order. Ascending? I don't know. Ascending and descending always confuse me. I'm sorry about that. And then select just the artist, the date entered, the week, the date, the rank, and show me the first 4 rows. And so what we'll see is the date entered is February 22nd, 2000. And this is its first week. Now the date is this column that we created, which is our date entered plus this calculation about the week. So now we've just added 7 days to the date entered for each week. This works because date objects are already in days units, and we can just add 7 per week to the start date. So now we can prepare to plot over calendar time instead of just the amount of weeks that a particular track was on the Billboard Hot 100, like in our last plot. So now we're going to create our plot by day plot, where on the x-axis we have the date, which we've assumed is just going to be like a week from the date entered for as many weeks as a particular song is on the chart. Y is going to be our rank, group is going to be our track. And here I've done some, made a geom line, and I've also added the month abbreviation using this notation. There's a notation for all of dates that are like this that I always have to look up every time I want to coerce something. But they're pretty easy to look up. So what I'm doing here is I'm saying for the x-axis, which is on dates, the date breaks is going to be every month, and the label is going to be this percent sign lowercase b, which is just the month abbreviation. And again, we're going to reverse the y-axis so that rank number 1's at the top. and we're going to use the black and white theme. And then we'll add lines for the start and end of the year using the geom vline layer. And we can just say that the x-intercept is going to be as a number, as the date, this character string that we are going to coerce into looking like this with the color equal to red. We'll get into a little bit more about coercing strings in week 8. And so now what we get is, instead of looking at just the amount of weeks that a song was on the chart, we can look at the year, including all of the time that is in our data. So now we can see some entry dates are like way, way before 2000, like all the way in June of 99. And some songs go all the way through till, looks like, almost May of 2001. Okay. So to practice working with finer grained temporal information, let's look at one day of Seattle police response data obtained from the data repository that Seattle maintains. So this data is a little bit older now, so I'm not sure if this link will lead you to the same place, but the CSV I'm using here is just housed on my GitHub, question mark? Sure.
Why is the month label B?
It's part of just like the a convention from like really old coding, that if you want it to say down here JUN and JUL instead of like the full month name, that you use % lowercase b.
Oh, okay.
Mm-hmm. Okay, so this police response data, it has 700 rows, 19 columns. It's delimited by a comma. It has 13 character columns and 6 doubles. So if we take a glimpse at this data, yeah, did I talk about glimpse already? Have we used glimpse before? Okay, glimpse is the tidyverse version of structure. So it's a lot easier to look at than STR is when you're looking at data frames in particular. And I think tends to just be a little bit cleaner looking. Yeah, and it also separate things like the column names into backticks if they have spaces in them, sort of like when we want to put backticks in things later on when we're plotting something, for instance. It'll also put things that are character strings in quotes to remind you that they're character strings. I don't know. It's got a lot going for it. Yeah, so I highly recommend glimpse over structure for most things that you would like to do. So let's talk LibreDate. Let's look at the structure of the dates that are given in this data set. So we have this event clearance date, and it'll tell us the month, the day, the year, the hour, the minute, the seconds, and the time of day. We want this to be in date time format, which is called POSIX-CT, not character. We will be working with dates using the LibreDate package, which again makes it a lot less of a hassle. And one thing that you can do is parse a date using these functions that are process date times in the order that they appear in the data. So here we're going to say assign to this SPD object the SPD raw data, and then mutate event clearance date. So we're going to overwrite our event clearance date is equal to MDY underscore HMS, our event clearance date, and our time zone is going to be the Los Angeles time zone in America. So what's going on here is month, day, year is this underscore is this space, and then hours, minutes, seconds is this information. And this function will convert this string into POSIX time. So here, when we do structure, it's now in POSIX instead of in character. And you'll see that it's written in the order of slowest thing first. And that's one of the main tells that we have a date. So slowest thing first being it's year, then month, then the day, then the hour, then the minute, then the seconds in that order. But it will figure out separators for you. The typical way you had to do this in the dark ages was to use these kinds of strings and know that the capital Y means 2000, all numbers, and then use the same separator between each thing in order to coerce things to be a date. But LubriDate just does that for you and will change its, will still do the job if there's a change in the separators between each of the things. It's really great. So an aside on time. Time data are a bit weird, as we've been talking about just now. R uses two primary formats for storing data on times and dates. First, there's POSIX CT. This is a numeric vector of seconds since the beginning of 1970. And this is the way that it calculates all of the math for those particular objects. So like when you want to just like add 12 days, it bases it on this vector of seconds since 1970. And then POSIX LT is a named list of vectors containing lots of date time information, including things since before 1970. But you can, I think, coerce POSIX CT to also deal with before 1970. But don't quote me on that. We typically use stuff after 1970. So we'll use POSIX CT. LubriDate gives us many convenience functions for dealing with date time data. It's often easiest to convert time to standard numeric values and work with it that way. However, particularly if it will be used as a variable in a statistical model. And what I mean by that is like earlier in the Hot 100 data, like we converted minutes and seconds to just minutes. That kind of thing makes it so much easier to work with than dealing with all of the differences between hours and seconds and minutes and days for a lot of procedures. So like sometimes it might not seem worth it, but you probably could just like convert all your dates to seconds, starting with the first date in your data set. It depends on the nature of your data though. So a few useful date and time functions. One is this as dot date is the base R function for converting a date into a date object. So converting a string into a date object. And it's okay. Sometimes it'll get the job done once you specify a time zone or some other information that maybe you don't have access to. But I tend to use the LubriDate package to do it instead. Other things you can do is say assign to a days of the week only object, the weekdays function, and then our two dates that we've made up here. And it will just tell you like, hey, it's Friday. I feel like that's really neat. You can also do things like say 1 hour later, assigned to that are dates plus D hours. So this is saying duration in hours, 1, and it will just move time up 1 hour based from when this date was occurred to begin with. Note that like here doesn't include the time because we used as.date and didn't specify the time, but this original data does have the time. So it's able to add an hour. So now we can do things like say, what time of day were incidents clear? So we'll say to the SPD times object, assign the SPD data, and then select the initial type group and the event clearance date and then mutate the hour equals the hour of our date time POSIX object or column. And then we'll make this time SPD plot by using ggplot, our SPD times data. Our aesthetic is going to be on our x-axis, the hours. We're going to make a histogram with a width of 2. And then we're going to facet by the type group, which is like the type of incident that the SPD is responding to. And make it look nice. So here we can look at event clearances on March 25th of, I think 2015, maybe 2016, by the hour of the day. And on the y-axis, see the count of incidents. So lots of things like parking violations here, traffic calls, that kind of thing. Let's talk about managing factor variables. Factors are such a common and fussy vector type in R that we need to get to know them a little bit better when preparing data. The order of factor levels controls the order of categories in tables, on axes, and in legends, and in facets in ggplot2. So what happens is it will quietly assign character things to a factor in order to order them. Often we want to plot an interpretable and aesthetically pleasing order, something like the highest to lowest values, and not just Alabama first, as is often the case when you're at like a conference roundtable or something. The lowest level of a factor is treated as the reference whenever you're doing a regression, and other levels get their own coefficients. Reference levels are by default alphabetical, which doesn't necessarily coincide with the easiest to understand baseline category. For instance, Alabama first, it's not always most prudent when you're doing some sort of analysis of states to make Alabama your reference category. Often it's like California or New York or something, one that's like especially different. Here's the forcats package. This is the tidyverse family of packages, includes the forcats package. It's an anagram of factors, and it also says for categoricals, because they're nerds and they name things goofy. This package supersedes the functionality of the base factor functions with somewhat more logical and uniform syntax. So check out the forcats manual when you get the time. So let's talk about converting characters to factors. So we're going to load the forcats library. And if we look at the structure of our initial type group, we'll see it's a character vector or a character column that is things like theft and trespassing and crisis call and so on. So let's assign to the SPD times data, and then mutate to create the initial type group column, rewriting it with a factor for initial type group. And we'll see that now when we look at the column, they'll say it's got 30 levels. And the first one is animal complaints because it has taken them and made it into alphabetical levels. So again, if we wanted to run a regression with this, animal complaints maybe isn't the reference category we would want to use. And then we can see as a numeric, this information like theft, trespass, crisis call is 25, 25, 28, which is just like its space in the alphabetical order as a number. So the forcats package lets us reorder and re-level our factors with a lot of efficiency. One thing we might want to do is reorder the factor levels by the frequency they appear in the data. So a really strong function for doing this is FCT underscore infrec, meaning like factor in frequency. And so now we can mutate our initial type group to be factor infrec, and look at the levels of that, or look at the head of that. And our most common one will be suspicious circumstances. And second most common is traffic related calls, and then theft, and then disturbances. So the most common levels being first means it's really easy to look at when we make it on a plot. So we're going to plot this data, and it'll look like this now. And so this gives us like the most common information up front. So things like suspicious circumstances and traffic related calls, and less things like person injury or prowlers. Does that make sense? Cool. There's some other ways we might want to reorder things. A general way to reorder a factor is with the factor reorder function. And the way that this works is you take, supply to the factor reorder function a factor vector, then the quantity to order it by, and then a function to apply to the quantities by factor. Okay, I'll give you an example here. This is especially useful for making legends that go from highest to lowest value, visually using like the max function, or making access labels that go from lowest to highest using something like the mean function. You can also use the factor relevel function and use the ref argument to change just the reference category right quick. So maybe you do want to just like, let's say you're running an analysis on like, I don't know, states, and you want to switch it from California to New York. The factor relevel function makes it really easy to switch those. Okay. So here's an example of reordering about JZ. So we're going to make this JZ object using our Billboard 2000 data, and then filter to the artist JZ with the dash. And then mutate the track is going to equal to track as a factor. And then we're going to make a plot called JZ bad legend and assign to it this GG plot with weak on the x-axis, rank on the y-axis, and we're going to group and color the tracks. And it'll look like this. And it's not necessarily the worst thing in the world. I think we can get this information. Anything was like mid JZ. Hey Poppy was like, okay, Jay-Z, but like, I Just Want to Love You was incredible, right? It was great. That's when like Pharrell and the Neptunes were really coming into their own. Lord Willin had not yet come out. NERD was not yet a band. This was like a big time. But if we want better ordering for Jay-Z, one thing we might want to do is first make a new column for our track. So we're just going to overwrite our track column and then reorder the track column, or reorder the track factor by the rank and the minimum value of that, and then run the plot again. And so now our legend makes a lot more sense, because the thing that's on the top of the graphical space is also at the top of our legend. And it took us one line of code to make this like way more aesthetically pleasing and easier to read. Because it's probably the case that you're only interested in Big Pimpin' and I Just Want to Love You. So let's talk about some dropping unused levels. After subsetting, you can end up with fewer realized levels than before. But old levels remain linked and can cause problems for your regressions. So like, let's say you were running some regression with all of the states, and then you have some particular notion that you only want to look at the Pacific Northwest. Your factor variable will remember that like Florida and Massachusetts are part of the factor's levels. So we might want to drop unused levels from variables or from your entire data frame. One way to do this is by using the drop levels function. So here we'll say JZ's biggest and apply the assign the JZ object, and then filter to tracks % and %. I Just Want to Love You and Big Pimpin', because of course that's all we're interested in. But the levels of this will still have things like, hey, Poppy. So now we can assign to Jay-Z's biggest, and then drop levels. And now the levels of this column are just the the two instances that we actually have data for. Okay, on to talking about your homework. So the homework for this week is actually in two parts, with the first part being due next week and the second part being due the following week. It's vote tallies in King County from 2016's general election, and they're in a 60 megabyte comma delimited text file that's downloaded from King County. They can be found on the course website. The data have no documentation aside from what I've provided. So show your detective work to answer some questions about the data and clean them up in the R Markdown template on the course website. You can command click on a Mac or right click on Windows to download the RMD to a folder you plan to work from, to open it in RStudio and make that your working directory. This homework is in two parts to be completed in each of the next 2 weeks. It can be daunting, so do not wait until Monday to start. I recommend reading the instructions closely, working with others, and using the mailing list and the Slack. And one thing to note also is don't open it in a browser. It's like a pretty big file. So just right click and save link as, and save the text file somewhere and load it into your homework after that. Similarly, instead of making this a downloadable link, I've made it just a text file. So one of two ways you can get this into your R instance is to copy and paste this document. And another would be to save link as. And you can actually, it says text document here, but you can just say .r and it will now become an R document. Yes. Yeah, so actually what's going to get put in the homework part 2 template is just going to be the homework 1 key.
Oh, okay.
Yeah. And then a note about next week. So I'm going to be out of town and sparsely available for email and Slack. That doesn't mean don't email me, but it does mean I might be slightly slower to responding to emails and Slacks. I will be providing recordings of the lab and the lecture for those weeks, or for that week. The RMD has a part 1 and part 2, just the part 1 for this week, correct? That is correct. So just the part 1 for this week is due. So I think it's, it'll say stop. That's it for part 1. So when it says that's it for part 1, you don't have to go on to the part 2 part. Yeah. So I'm going to provide recordings for the lab that would have taken place on May 3rd, and they'll be posted on May 3rd. I'm just going to record them ahead of time and then make the YouTube page, post them the day of. The same thing will go for lecture on May 5th. So I'm just going to make a recording available for those. Trying to think if we have any other questions or anything else to cover. I will not be having my usual office hours on May the 4th. Kind of a lot of stuff happening that week. May Day is May 1st. May the 4th be with you. Cinco de Mayo. Thank you, Veda. Yeah, I'm getting married on the 7th. Yeah, big week. Yeah, do we have any other questions? Thank you, Hannah. I appreciate that. It should be a good time. I had a really, what's up?
Oh, that's what you would want to hear before you get married.
Yeah. Yeah, it's expected to be a good time. yeah, so thanks everybody. I'm gonna turn off this recording and all that, and y'all have a good one.